an applied mathematician with focus on geophysical flows, and she will be talking to us about essentially ocean modeling in the Eastern Mediterranean. Leila's work has been quite daring in actually taking on data for the Eastern Mediterranean and integrating it within mathematical modeling. And I'm personally quite excited about her work, her project, and looking forward to collaborating in the year to come. Thank you, Leila, for agreeing to give this talk, and very much looking forward to it.
Thanks, Ihad, for the introduction. And thanks everyone for coming. It's a real pleasure to be here, and it's a real pleasure to be within this small community of CAMS Fellow. I'm very looking forward to opportunities of collaborative work, and for this space that allows me to launch ambitious project on the scale of Lebanon. So I'm really excited about this. So I'm going to tell you about this area of research that I started about 10 years ago. And the irony is that I was in France in l'Océan Laboratory, which is a multidisciplinary lab, computer science, oceanographers, and applied mathematicians. And within my collaboration, I found out that the Marine Center in Lebanon recently acquired drifters, and they were going to launch them off of Beirut. And they had also previously acquired a boat named the Kana boat, and they were going to use this boat to launch the drifters. But they were looking for people who could do physical-based modeling to use these drifters to understand the circulation near our coasts. So the irony is that through the European, I met somebody in Lebanon who wanted to do this. And so then started a project called Altifloat, which was funded by the European Union. But then this interest in this research grew out of this specific project, and I'm going to tell you about it today. So studying transport in the ocean is a problem of global and local relevance because of the environmental consequences that it has. So this is like a sensationalist slide where we scare people with numbers. So if you think about plastic pollution in the ocean, according to the UNESCO, according to a report that was done last year, they expect that by 2050, plastic will likely weigh the fish in the ocean. And so this is a picture from the plastic pollution in the Pacific. And this is a local picture that was taken during the garbage crisis in Lebanon in 2017. And so what we really want to understand here to understand the consequences of this disaster is we would really like to know how much is concentrated where and what are the mechanisms that allow these pollutants to go from one place to another in the ocean. Another application include release of contaminants, oil spills, and these could be accidental or premeditated, like the aggression that happened in 2006 and that led to the GE spill. So this is a radar image that shows that how the spill was more or less localized between off the coast of Lebanon in July, and by August it had spread way north of the coast of Syria. Okay, another consequence of the transport in the ocean is to understand what's called algae blooms, and this is a problem of ecological relevance. So, for example, we would like to understand how the nutrient-rich coastal water transports these nutrients to the more oligotrophic waters in the open sea. Let me show you. So this is not clickable. Anyway, I'm going to show you a similar picture later. So don't worry about that. So let's talk about the main physical mechanisms that are responsible for transport in the ocean, and that will allow us to write a mathematical model that represents it. So, so there are two main mechanisms. There's advection by the underlying flow that's transporting the tracer. So this process is the process by which a tracer is transported from one location to another while it's being carried by the flow. But there's also diffusion, and diffusion can be of two kinds. There is molecular diffusion, and it's a mode of transport that is associated with the random motions of the molecules. But there's also what's called in the ocean turbulent diffusion. And turbulent diffusion is the effect of these small eddies in the ocean. So they are eddies at a much smaller scale than the big ones. And so their effect is to actually have an effective diffusivity that is much more important than the molecular diffusion. Okay, so here I'm illustrating a simple advection scenario. So this is 1D advection. This is uniform transport by a constant velocity. So you have the initial bump that moves, in this case, to the right and remains unchanged. And on the top right, I'm illustrating diffusion. But in general, in the ocean, things are much more complex than this. So you have a real complex flow that has multiple scales in it, that is non-linear. So what I'm showing here is a simulation of an advection by an Ekman flow. An Ekman flow is a flow that is wind-driven, and that is valid in the first 100 meters of the layer in the ocean. And you see that in this flow, for example, so on the left, we trace the set. So if you have a patch of substance that initially starts at a certain location, on this diagram here, we are showing the advection of its center. So we see how it's moving, the location, and it's spiraling up according to this Ekman flow. But also, as it spirals up and moves, we see how it diffuses and how it rotates, or it's sheared, or it's deformed by the flow. Okay. So mathematically, we can assemble these physical phenomena by an equation called the advection diffusion equation. So here, this is the S is the concentration of the tracer that we're interested in. U is the velocity field that carries this tracer. A is the diffusion coefficient, be it diffusivity or molecular diffusion. And we are working, and we could be working on the surface of the ocean. So we would be really in a 2-dimensional domain, or we could be working in a layer. So we would have a 3-dimensional domain. We could be in the open ocean, so we would have an unbounded domain, but we could also be interested in the boundary effects, the coastal, or the interaction with the 2 boundaries of the ocean that are the upper layer and the bottom of the ocean. Okay, so this is a general formulation. And of course, we have an initial condition that tells us the initial concentration that we have. Okay, so the first contribution of this research concerns this velocity field U. And it's about a continuous estimation of this velocity field on the surface, with special attention to what we call the Levantine Mediterranean, which is the eastern part of the Mediterranean. I'll show you in a bit on the map. So what we've done here with my collaborators is that we came up with a variation of assimilation algorithm. Assimilation means that I assimilate data into a model, as I explain soon. And specifically, I assimilate drifters data to a simple advection model to better characterize the surface circulation, as I said, with special attention on the eastern part of the Mediterranean. And after this algorithm was developed, what we did is that we validated it with an independent data set. So that is not the data that we used in the assimilation. Specifically, we validated this algorithm with the current meter data, gliders, and ocean color. All of these are tracers in the ocean. And finally, I'm going to show you how one can use such an algorithm to characterize local events, such as the Ira-Petra eddy, which is an eddy in the south of Crete. Okay. Okay, so just to tell you how nowadays the abundance of observational tools of the ocean have really evolved us from a very basic understanding of the circulation in 100 years here. So this is a before and after picture. So 100 years ago, we could just look at the basin scale circulation. So what you see is that these arrows are flowing counterclockwise. And the reason this is happening is that the Atlantic water is coming to the Mediterranean because in the Mediterranean, the evaporation is much stronger than the precipitation. So the Atlantic waters comes in, and as it comes in, it becomes more dense and salty. And the main effect that makes it circulate this way is the Coriolis effect, which is the rotation. But now with the many observational tools, as I will show you, now we can understand more. So when we look at this picture, so first of all, this is a defining box where people in the community define the Levantine Mediterranean or the Eastern Mediterranean. Levantine is a bit of a Orientalist term. Some people call it the Levantine, some people call it the Eastern Mediterranean, and that's our area of focus. And inside it, you see these small loops. So these are vorticities, these are called eddies. They are eddies that are on a smaller scale than the big, if you wish, you could call this circulation pattern above a gyre. Eddies have typically diameters anywhere between 50 meters and 200 meters, whereas gyres are much larger. So you could think of these eddies as like the local weather of the Mediterranean. And that's what we're trying to do. Okay? So when we say mesoscale to sub-mesoscale feature, we are referring to this median scale. And one thing you notice, what do you notice about these eddies in the way that they're circulating? Yeah, it's not the same as the big gyre, because here the effect of there are effects that are not just the effect of Coriolis is not present because of the scale, because this is at smaller scale, and I will explain that later. Okay, there are smaller scale effects that make it rotate clockwise and anti-clockwise. Mainly, it's the difference in temperature between the center of the eddy. The inside is made of cold water, whereas the outside is made of hot water. It makes it go in this anticyclonic fashion, and vice versa.
For now, the size of these circles is not to scale.
No. This is just diagram.
Just an indication of the
location.
Yes. The location.
Yes. And so, so to be more specific, these are coherent structure that last at least 6 months to 1 year, but could last more. So, for example, this is called the Shikmona eddy. This is called the Cyprus eddy, and this is called the Irapetra eddy, and this is called the Marsa Matruh eddy.
Leila, in this, what is the next scale of
50, anywhere between 50 and 200 kilometers. Yeah, sorry. Okay, so I'll come back to this slide later. So I don't like that this is masking the title of the slide. Is there any way about it? Or is it just the Zoom people see the title and we don't? Doesn't really matter. I'm not gonna mess it up. Okay, I know the title of my slides, so I'm not gonna mess it up. Okay, so what are observational tools that allow us to have this coverage of nowadays oceans, specifically as well? So we have 3 types of observations. The first is called in situ. In situ is a Latin word, nature plus, like where I am. And among in situ observations, we have drifters. This is a picture of a drifter that was launched off the Lebanese coast. And these are smart buoys that float on the surface of the ocean and that get carried with the surface currents. And then they communicate via satellite their position at discrete time intervals. And they are dropped, and the drop allows them to not be affected by the wind, so that they're not pulled off the surface layer. And these specific drifters go at depth of 15 meters. And these are the type of in situ observations that we will assimilate in our method, as I will tell you soon. We also have gliders. Gliders are underwater robotic instruments. They go in depth, unlike drifters, so they can park at different depth, up to 200 meters depth. And they also measure absolute geostrophic velocity, salinity, temperature, and so on. Finally, we have moorings. Moorings are a collection of devices that are attached to a wire, and they are anchored at the seafloor, and they have different instruments that go off. And one of them is current meters, and current meters measure the velocity where at the corresponding part. Okay, among other things. All right. Now, if you look at this figure here, this figure shows the limitation of in situ measurements such as drifters. Because these drifters, sometimes they hit the shore and people throw them away. They are not long-lived. And so there are gaps. So if you look at, although over the years, these gaps have become better and better, you have to see underneath this. So before the gaps, we had more gaps. The reason is that now there is a lot of funding in specific programs that cover certain areas of the Mediterranean, and the people are launching more and more drifters. Okay. All right. Another type of observations are satellite observations. The most common satellite observation system that monitors the surface currents is altimetry. And the principle of altimetry is that it measures the sea surface height from which the geostrophic current can be inferred. This has to do with, so what is the geostrophic current? So currents are governed by the Navier-Stokes equation, which has a lot of physical phenomena in it. So it has acceleration, it has wind stresses, it has Coriolis, it has gravity, and it has pressure gradients. And at certain scales, which is the basin scale, let's say in the order of 1,000 kilometers, the dominant balance in this equation is the one where we equate the Coriolis force to pressure gradients. And vertically, we have the hydrostatic balance, which tells us how the pressure varies in the vertical direction proportional to gravity. So if you look at these two equations, they allow you to extract surface velocities from the seawater elevation by integrating the hydrostatic equation from the surface. And that's what geostrophic currents are. So we have these satellites that by radar can measure the sea surface height by sending a signal to the surface of the Earth. And this is nice because it provides a continuous coverage of the oceans nowadays. It's literally non-stop. Maybe they have daily values provided, but it doesn't have any gaps, unlike in situ measurements. However, its shortcoming is that it only provides accurate information on the scale of 100 kilometers, which is the geostrophic scale. So for example, if you would like to resolve structures that are local and that are smaller in scale, it's not very efficient. Okay, so here's an example of a simulation that illustrates the shortcoming of altimetry. So what's going on here in this picture? We have three trajectories that are along the Lebanese coast. These are real drifters trajectories, and these are the drifters that the Lebanese CNRS launched from the south of Beirut. And on this side, we have the drifters trajectory simulated with the geostrophic current from altimetry. And you see that it's completely off. It's taking that inwards, whereas the real trajectories are the ones that are along the coast. So this reinforces the fact that altimetry near the coastal areas is inaccurate. The other thing to see from this picture is the difference in the nature of the data, because the altimetry data is an Eulerian type of data. It's given at certain grid points, whereas the drifters data is a Lagrangian type of data. It goes along the trajectory. Okay. All right. Another type of satellite observation is ocean color. So how do we get ocean color? We get it by detection of reflectors, because the nutrients, especially chlorophyll, which is present in rich water, changes the reflectance property of the water, which changes its color. So this is a snapshot of a chlorophyll concentration in 2012. So you see here that you could see an eddy. So this is really acting like a tracer. But then again, it has its main limitation is that it has a discontinuous coverage because of the clouds. So if you look at this picture, this is a good day. This is a good end of summer day where the clouds are not that present. So if you look at these pixels here, they are masking the image. These are clouds that mask the image. And this happens frequently with chlorophyll data. You cannot get a continuous sequence of images that are not masked by clouds. All right. Now, the final observation tool that I'm talking about is ocean's general circulation models. So what are these? These are numerical solutions to the Navier-Stokes equation that I was telling you about. And people in the community call these equations the primitive equations. So basically, these are Navier-Stokes equations, which are conservation of momentum and mass under certain assumptions. So what are these assumptions? There's a main assumption is the hydrostatic assumption. What that means is that if you look at the W component of velocity, the dominant balance there is the pressure gradient in the vertical direction balances gravity, whereas the rest of the effects are what has dominant. There's also the Boussinesq approximation, and that tells us that the density rho is constant except when it enters the buoyancy. Okay, and of course we have an energy equation, which is advection diffusion equation for the temperature. Same for salinity. We have the boundary conditions and the initial conditions. So there are many ocean circulation models running in the world to monitor the state of the oceans. I mentioned a few here, like MIT GCM, MEMO by the French, MFS, the Mediterranean Forecasting System, which is a European project mainly maintained by the Italians. And what these models do is that a lot of these models depend on parameters. And the idea of parameters in this model is the following. So there are a lot of small scales that are not really understood and not resolved. So they end up being parameterized. For example, turbulence. And the main limitation of this model is the ability to resolve these parameters. Okay. So the other thing I wanted to say is that typically these models, when they're run, they do data assimilation. So they assimilate all kinds of previous observation into fine-tuning parameters. Okay. All right, so now we come to the idea of data assimilation. So what is data assimilation? We can think of data assimilation as an optimal way to fuse all these sources of information. So what we want to do is that we want this observed information to be accumulated in the model that we are considering. And depending on which community you are, people sometimes call this PPE constraint optimization, especially if you're talking about a dynamic model, like the models that I mentioned previously. These are numerical models for solving PPE. And that's what constrains minimization. And what are you minimizing? You are minimizing the difference between the observations and the model that leads to. There are many flavors of data assimilation. So this is a nice diagram from these nice lecture notes here on data assimilation. So they are separated in terms of real-time assimilation. In real-time assimilation algorithm, you use the past observation to predict the state now. This is what happens in real time. Whereas you could also use retrospective analysis. That means you could also use future observation to reanalyze what happened in the past. Okay, and that's what also people do in these data assimilation schemes of numerical models. They could do reanalysis, they could revisit the past and find the parameters, they could do predictions, and they could do analysis. Analysis is a if scenario. Okay, there are two main methods of data assimilation: the 4D bar and the Kalman filter. The Kalman filter comes with many flavors: the extended Kalman filter, the ensemble Kalman filter. But the basis is really control theory. The mathematical basis is control theory that was developed by Lyon in 1968. So I'm going to focus on variational data assimilation because that's the method, that's the algorithm we developed is within this umbrella. So as I said, the idea is that we're going to minimize an objective function that measures the misfit between the observations and the model observation. So as if I was running a model that predicted those observations. And what makes these, so there's in this community 3D versus 4D. And 4D is when the observation are time varying and when the model is dynamic. As soon as the model is dynamic, it's called 4D. And because you want to minimize an objective function, you would need for the optimality condition the gradient of that objective function with respect to control. So here's where adjoint type methods come into picture. So adjoint techniques are an efficient technique to calculate the gradient. It's basically on the chain rule, on smart implementation of the chain rule. And so the theory is very well developed, but it took a while to introduce these methods to apply them to atmospheric and oceanographic predictions. So that happened later in the 70s in the atmospheric community and in the 80s in the ocean modeling community. Okay. So 4D, so we're going to call it 4D bar, and 4D bar is really computationally expensive and risky if we don't do something about it, because simply the objective function that you're trying to minimize may not be convex and may not have a unique minimum, especially when the model is non-linear. And what really saved this method and made it computationally feasible is something called the incremental approach. So as this picture indicates, if my objective function was quadratic, then everything is fine because I have complexity, right? So the idea, even though I have an objective function that could do anything at once, I'm going to locally approximate it by a quadratic function, which means that I will take my model and linearize it around the background state. And then I could deal with the optimization in each step in this way. Okay, but every time I have to be around the background so that the linearization is done. So that's called the incremental approach. And now I'm going to summarize the algorithm we came up with. So now the idea is that we have these observations of the drifters we want to assimilate, but we're not going to, although we can assimilate them into a numerical model, whereby I run a variation of that space. Simply because what I could do instead, I could start with a background that is asymmetry, which is an observation of the geostrophic field that I want. So that makes it faster, because I have it ready, I have it every day, I have this background. And what I want now is a simple model that relates this geostrophic field to drifter's position, and this is advection. Because we know that the rate of change of the position of the particle or the tracer is the field, the Eulerian field evaluated at that position. So that's the advection equation, which is nonlinear. But I also need interpolation, because where I have the background field is on the Eulerian grid, but I really need to match that with observation. which is the Lagrangian information I have. So this model consists of discretizing the advection equation with a scheme like RK4 or Euler or whatever you want, and an interpolation operator. And it also involved linearizing it around the background state. So writing the linear tangent model, that's what we call it. And then we can run the optimization, because now we can compare these model drifters' position with the actual observation. And what this spits out is a correction of the velocity field that is supposed to improve on the background. Okay, so this is the objective function I'm talking about. So here, this is the linearization, because you have a background. So you have positions predicted by a background, and you have a perturbation on top of it. And what's to notice here is that this is linearly dependent on delta U, which means now you have, this is quadratic, everything is quadratic. Okay, so the first term tells you that you want to minimize the distance between the model and the observations. The second term is what's called, the second term tells you that you also want to minimize delta U, which means you also want to stay close to the background. You don't want to depart too much from the background. But it also takes into account what's called the error in the background. So you have postulated that the background is the geostrophic field, but you could be in error. And the error corresponding to that is taken care in what's called the error covariance matrix. So this is a norm whereby you take delta U, you do delta U be inverse delta U. And the third term is to ensure a physical correction and to avoid numerical artifacts, because we're assuming that the field is divergence free. So the third term minimizes the divergence of the correction. Okay. And okay, the other thing about this scheme that we came up with is that for a time, so this is a 4D bar scheme. So we're doing the minimization in the time window, whereby we have many observations contributing to a single correction of the velocity. To make this continuous, what we do is we move the window. So we introduced a time-moving window to obtain smoother corrections. So if you're at a point here, you have many windows of moving drifters contributing to this correction here, and these are weighted by the highest weight is put on the window that is closest to the actual point where you correct. So what this in effect does is that it provides a continuous correction, a time continuous correction, a smoother correction. Okay, so the first thing we do when we have this algorithm is what's called sensitivity analysis to fine-tune the parameters of the algorithm in a specific region that you are applying it to. So this is where the specificity of the region comes in. So the algorithm itself is not specific to being applied in the Mediterranean or in the Atlantic or anywhere else. So in this sense, it's portable. However, the optimization depends on parameters that are highlighted in blue. So first of all, there's the weight that you put in the for the regularizing terms, alpha 1 and alpha 2, with respect to the observation that is normalized to 1. There's the size of the time window. How many observations are you going to account for to create a correction? And there's how you shift the window, the time shift. And there's the parameter of the error covariance matrix. The error covariance matrix in this case has a Gaussian in it, and the support of the Gaussian is a parameter in this. So here's the sensitivity experiment that allows us to fine-tune these parameters in a specific region. So what we do is that we have a set of drifters. We separate the drifters into two sets. The drifters we're going to use for the assimilation, and then the drifters we're going to use for the error computation or the comparison. So what we're doing, we're assimilating a set of drifters and then obtaining a corrected velocity field. With this corrected velocity field, we simulate drifters and we compare to the other set. And by minimizing this error, we fine-tune the parameters. So here the metric that we use is the mean separation distance between the trajectories obtained by, these are the ones that have the assimilation in them, and these are what we consider observations. Okay, so we can fine-tune our parameters this way. And let me show you an example of an assimilation. How does it work? And here I have to look here and go to the player. Let's see if the player is in the right. It's not playing it. Okay, so the black is the drifter, that is the actual observation. The blue is the background. Oh, this is faster. And you see that this is a local correction that extends a little bit in time and space. So where am I correcting? Of course, I'm not correcting there. I'm only correcting around where I have the drifters. But I'm not just correcting technically in the vicinity of the drifters. I'm extending this correction in a radius around this drifter. Okay? Yes.
It's a good plan to ask this question. You showed us a figure which was sober. Showing how corrections to vectors would be order one.
Yes. Yes.
To carry vectors
That's true.
of.
Yes,
So,
that's
and
true.
now you are proposing the corrections to algebraic flows. So this has a specific region over which it operates drifters that are captured in these flows as opposed to.
But
Do you
it's
have
not just-
caveats to its applicability, or is it? Or do you
So-
feel that it's gonna do the right kind of correction close to the coast?
No, that's the thing. It's not just the correction is dramatic close to the coast. So the two things.
So when you say correction, you're allowing for order one correction. We're not talking about adjustments.
Yeah, because the flow next to the coast is HSO.
That's what I
So-
mean, so.
But
that's
you're not
precisely
just correcting that. Even in the middle of the ocean,
what I see.
where the flow is just perfect. Algebraic has a lot of errors. For example, it's known that algebraic can underestimate the intensity of the error.
It's just to point out that you're working with linearizations and the effects you're talking about will be quite dramatically different from the flow you start out with.
You mean, okay, yes, but. Okay, but I'm bound, since I'm bound to start with the
Yeah, you're
so
bound to
this is
start
my
there.
background.
Yeah, you're
And
bound.
there's a term in the objective function whereby I have to account for being needed. I cannot really be that far off. So it's a compromise.
So you could go way off still closer to the coast.
True, but then that means you cannot run it for a long time.
Okay.
The thing is, you cannot.
I'm just
yeah.
getting clear
Yeah,
because
yeah.
you
Okay,
reminded me
so-
of something very important, and I'm trying to correlate it with the
Yeah.
methodology you use.
Yes, but the thing is that I'm not, okay, so when I'm next to the coast, I'm not running this, let's say, over a month. Every time I would run it over a time window that's not exceeding 52 or 3 days,
Okay.
because that's a Lagrangian time scale.
Okay, so now
And then I
understand.
restart.
I understand. Okay.
If I didn't restart, then you have, then I wouldn't even convert actually.
Very good.
Okay. So. Okay, so now, so this is the kind of internal fine-tuning of the parameters of the methods. But now what we did is an external validation of the method using data that has not entered anywhere in the algorithm, anywhere in the assimilation. So this was an exercise of finding such data Oh, okay. He wants full view. It's- Okay, so here we have to look at this external data that coincided with the passage of drifters. Because as we said, drifters have gaps, so you could be looking at different data where there are no drifters, and that defeats the point. So we've looked at mooring of a current meter that was 60 meters deep. That coincide with the passage of a drifter. We looked at chlorophyll images, and we look at glider data that was also near drifters that we could use. Okay, so we start by showing the results of this validation with the current meter data. The first thing to note is that the current meter is at 60 meters, whereas the drifter is at 15 meters. So what we did, so the variability, the vertical variability actually depends on the signal, on the winds, on many factors. So the first thing we did is we looked at outputs of an operational model to look at the vertical structure of the current and to see that really there is no variability in the period we want, and that was the case. So we could allow ourselves to compare currents at 60 meters versus 15. And so there was one drifter that was circulating. The location of the black arrow shows where the current meter is. And let's quantify these corrections. So what are we seeing here? The first plot shows the distance, because the drifter is moving, the current meter is fixed. So as the drifter moves, it drifts away from the current meter. So this shows the distance between the current meter and the drifter. And then what we show as a quantitative way of measuring the error is the L2 norm of the velocity, which takes into account the zonal and the velocity. So we have two colors here. We have first the error between the current meter and the background, the altimetry in blue. And then we show in red the error between the current meter and the assimilated velocity. But we also show not just magnitude, angle, the orientation of these arrows, and the same thing. So the same thing, the blue is the background, the red is the corrected. So if we were to quantify these results, we would say that within 30 kilometers distance with the current meter, we're looking at about, let's say, 30% improvement in terms of error. And the natural thing to observe is that as the drifter moves away from the current meter, the effect of the assimilation becomes less and less. And the same thing can be said for the angle. This is where we have the biggest correction. It's for the drifter is within 30 kilometers of the current meter. So one could extrapolate these results to say perhaps how much we are really enlarging the space of correction around the drifter, or to argue that it's an order of 30 kilometers. And if we were to compare this to the Rossby number in the terrain, that's about 3 points. Okay, so that's the first comparison. The second comparison is with this glider data shown in green. Although it looks like the glider and the drifter data intersect a lot, but it's fooling because they don't intersect at the same time. So there was only one drifter that circulated for 2 days only, at the same time where the glider was. And again, we show quantitatively the L2 norm comparison. So here we don't show the difference, we just show the velocities. So we can observe that the red is closer to the glider than the background, and that's also about 20% correction. Now here there are many reasons for this 20%. Again, the distance is an issue, the drifter is going to be away, but also The glider samples, the time sampling of the glider is different than the time sampling of the lifter. The glider has the data every 1 hour, whereas the lifter gives it every 6 hours. Finally, we have a qualitative comparison with a color image. So we have these drifters that are stuck in an eddy. And if we look at streamlines of the velocity field before and after correction, we notice that the streamline corresponding to the altimetric field are maybe to the right of the maximum concentration, whereas the streamlines of the corrected field are more in agreement with the eddy predicted by the corrected image. Okay, so what's after validation? How can one use such a method? One could use now such a method. We could perhaps go away. We don't need to stick to a certain area in the Mediterranean. So here we've gone more to the west level 9 Mediterranean. And we looked at characterizing the Iraq-Medfa eddy in terms of its mean kinetic energy and its vorticity. So we computed the mean kinetic energy of the velocity fields after correction and before correction, but we also compared to the output of a numerical model, which is the MFS, the Mediterranean Forecasting System, the geostrophic component. And the result here is that the assimilation accentuates the eddy more than the altimetry or the MFS. So it's widely documented in the literature that the altimetry tends to underestimate the mean kinetic energy. That's in agreement with that. How am I doing on time? Oh, I'm not gonna get to the part I like. Okay, well, skip to the part. Okay, yeah, I'm gonna skip to the part I like. So this is another way to look at this eddy by its vorticity. And so we could capture that. So this is a historic event when the relative vorticity exceeds the Coriolis. That has consequences on the eddy instability. And that occurred 3 times before in the past 22 years. And this method would capture the 4th time. And I'm not going to show you this, also the agreement with flow field images, eddy merging. That was what
So you captured that you mean, or captured that you mean. You carried out.
No, I did not predict it because this is in 2006. I captured it. Yeah. But it was not documented in the literature.
Wow, that's remarkable.
Yeah. Okay, I'm going to skip machine learning. I just want to tell you, if you want to do long time, these are short time characterization. By short time, I mean on the scale of months. If you want to do characterization of surface currents on the order of years, like 25 years, we've done some machine learning where we use the self-organizing map to basically put the surface circulation into clusters. Based on the Okubo-Weiss parameter. The Okubo-Weiss parameter is a parameter developed by Okubo, who's a Japanese oceanographer / applied mathematician, and it tells us it tells us how the strain and the stress compare to what is basically a positive Okubo-Weiss indicates that the flow is strain dominated, whereas a negative Okubo-Weiss indicates that the flow is vortex dominated. So I'm going to skip on that, and I will get to the second part of this current research that I developed with my master's students at LAU, and that is still in process. So now, okay, I know the surface currents. I can either get them from data or I could get them from a numerical model. I'm interested in simulating the transport of a tracer by looking at the advection diffusion equation in 3D. And the ultimate goal for me to actually estimate eddy diffusivity from tracer observations. But before I do the inverse problem of estimating the eddy diffusivity, I would like to have a forward scheme that is computationally feasible, because I'm going to give it to eventually to an optimization problem, so it has to be light, quote unquote. Okay, so this advection diffusion, although it's a linear equation, it doesn't have any closed form solution unless the velocity is constant, in which we get the heat kernel shifted by that velocity. And when I looked at the literature, I fell in love with that paper of Okubo in 1960, whereby he actually proved he could get an analytic solution for this equation, a fundamental solution. That means it's an open space, the boundaries are involved, and when the flow is linear in space. So what my master's student and I have done, first we generalized this form of solution to 3D, and what we eventually want to do is we want to employ it in a grid-free scheme to simulate this advection diffusion equation, because it makes sense if you are tracking a patch or a concentration. It makes more sense not to adopt an Eulerian way of doing that, because then you have to discretize a whole grid, but you just want your attention where the concentration is. So in this spirit, grid-free methods that follow the concentration makes more sense. And it's also traditionally known that grid-based method, when the advection dominates, they have oscillations and they need more and more grid refinement, and it becomes prohibitively expensive to carry such simulation. And my student actually experienced that, because we were comparing to a grid-based method like COMSOL. So for example, she would run, so for high clear numbers, she would run simulations that would take 20, 40 hours to end up with solutions that are very non-converging at all. Okay. So this is what we've done. This is what I said. We first extended this solution to 3D, and we are in the process of working on this algorithm. So let me tell you how we do that. So you're going to look at the same equation, but with a linear flow field, where you take the actual flow field and you use Taylor expansion to linearize it around the center of the path of interest. And what appears in this linearization are the local deformation parameter of the flow, because these are the derivatives of the velocity with respect to space. So again, we see those strain, stress, shear, and vorticity. And so once we do that, we could show that the solution is a constant. So that, what does that physically mean? That physically means that the contour of concentration are actually ellipsoids. And the major axes of the ellipsoids will evolve in time according to the local deformation parameters of the flow. So this is a classical, so the proof is really classical. You write the concentration in the Lagrangian coordinates, so that you transform your advection diffusion equation to a total diffusion equation on characteristics. In the case where the velocity is linear, you are lucky, because you could solve the characteristics equation. It's a linear system, you could solve it exactly. Then you could solve the diffusion equation exactly, the Fourier transform, and then you invert from Lagrangian to order. Okay? So that's the idea of the proof. So, however, when you do this last inversion from Lagrangian to Eulerian, and you try to collect these terms, you get monsters. You get monsters in terms of combination of the parameters of the flow. I'm just showing you an instance of this monster. Okay, you have the expression, you can validate it with data. But then you want to code it on a computer. It's full of singularities, all are removable singularities, but you really need to pay a lot of attention and care to even code this, which is a nightmare. So I'll tell you how we deal with that later. But what you can also get out of this solution is is what's called an apparent coefficient of diffusion. So what is that? That's a coefficient of diffusion that reflects the rate at which this differential advection by the flow magnifies the original diffusion. So it has the combined effect of the diffusion and the differential advection of the velocity field. So one thing we could show is the small time asymptotics of this apparent coefficient of diffusion and the large time asymptotics. So under certain combination of the parameters, and then again, this actually brings us to the Hugo-wise. We could show that it remains bounded. So as an example of such flows where you have rotational flows, and it makes sense because when a batch starts rotating, it slows down the diffusion. Whereas if it's stretching, the dominant is the stretching of the rotation, it's going to. So the diffusivity is unbounded. Okay. So another thing we could get out of this are three special linear flow closed form expression. I could envision using them as benchmarks. So if you are simulating an advection diffusion equation and you want an analytic solution to compare with, you have those, because then you can compare with an analytic solution for these special cases. And so now let me tell you what do we do about this analytic solution for the linear case. And let me tell you why we do that. So here's the idea quickly of the algorithm. How am I doing? Yeah, I'm going to stop soon. The idea is that I'm going to put this in a time stepping scheme, whereby I'm going to go from t to t plus t delta t, in which I can assume that the linear approximation holds and that the patch hasn't dropped too much. So I'm going to take an actual patch and I'm going to write it as a sum of Gaussians or approximate it as a sum of Gaussians. And also each Gaussian, I'm going to evolve it according to my solution. So now the idea is that if I go back here and in this proposition, what I'm saying, I don't really need to get these coefficients analytically. What I could do instead is just take the form of solution as an ansatz, substitute it in my PDE, and show that these satisfy a system of NPs. Because anyway, I'm between t and t plus delta t, I'm going to solve them. Okay, so that's the idea. And of course, the limitation as such in the algorithm is that at some point, these are going to start growing too much. So I have to intervene. I have to either remesh or redistribute, as is done in the distribution scheme. So finally, the last result I'm going to show you is where is this headed. So we compared with Console, which is a grid-based solver. And what we're showing here is that so often people in the literature in the redistribution scheme, they rely on the solution of the analytic solution with a constant field. Whereas now we are proposing a higher order solution, the one of the linear. So for the same error with Console, you can get away with fewer elements using the solution with a linear field than the solution with a constant field. So the hope of this method is that you're going to be able, if you do a proper redistribution, to use fewer elements than if you were to use the solution with a constant field, because it's a higher order. Okay. So I would really like to thank you for your attention. And there's some other problems that I don't have time to talk about. Specifically, I've also been working with people from past on identifying both responsible skills, manuscript interpretation, and also on a probabilistic approach to simulating transform with ensembles. And that's what I wanted to tell you today. So I will take your questions. Thank you so much.
Very much, Leila. You beautifully fulfilled the expectations of this series of lectures. Thank you very much.
So we have time for questions from the audience, and time from.
Yes, sir.
Just have one question related to the data assimilation. So now, are you using anything related to, say, data optimization?
No, not in this framework. Not at all. Everything is deterministic in the data center.
Very nice presentation. For the low field data, the images, are they high refractive data?
What does that mean?
So what is the kind of images that are taking care of the low field compared to?
So they measure reflectance and they map it to concentrations. So these are concentrations.
And what about like, you mentioned something about moving data
Yes.
somewhere, but I presume I'm moving data driven computational gradients.
Well, the gradient is the gradient comes from the optimality condition, from the optimization problem. We call this one. So you're trying to fit data from a model. So in this sense, you have an objective function you want to minimize, where the control is the correction. So you need the derivative of that objective function with respect to the correction. That is the gradient.
Yes.
Oh, the model I have, yes, I have the
So
model.
not a data driven.
No.
Not, I think, not, number one condition.
No. I have the model, so I could analytically write the direction model with the interpolation, and I could get it.
And you are using different types of sensor data. So you are doing something unusual, data about this, about objective, because you have like data at different sample days, data from different types.
Oh, yeah, that's it. Of course, yeah. So that's the main challenge in validating the algorithm is to be able to find. So this, let's say that this algorithm would be dead without difference. I wouldn't be doing anything if I didn't have difference. Although the methodology of assimilation would have difference. So since I'm relying on drifters, and since drifters are not everywhere at the same time, so this picture that I showed you is full because it's like a history. Then I have to find the right data that was there at the same time. That's the first challenge. The second challenge is that the observations, they don't map one-to-one with each other. For example, with Leila's data, is data average of depth. And also, the current is just stopping at certain different Leila's projected. So I have to project the Richter's data onto that. The current meter data, again, the issue is that they're not at the same depth, so I have to look at vertical variations. So it's not always a one-to-one map in terms of comparison.
That is what I think I should. The challenges of the data are too much. And a final question. So you can the optimization must come out of the light. The light, does this have to do with carbon?
Okay, so the main difference between 40 bar and Kalman filter, from my knowledge of Kalman filter, is that in Kalman filter, they both come from control. So the theory that we actually under linearity assumption of the model, it's just the way in the Kalman filter approach, as it was originally stated, you write explicitly the way. Write the updated solution in terms of the which I guess amounts to writing the normal equation of the least square system. Whereas in variational assimilation, you don't write it, you just solve the optimization problem. You find the optimality condition and solve the optimization. It's a smooth, so it has dual purpose. It tells you that you should stay close to the background, and it smooths the correction of space.
When you have measurement and you have a model and you have a measurement, so based on what is more certain, your measurement or your model that you can give more data.
Yeah, but this is in this objective function is more or less the same because you can control those factors.
Okay, let's postpone until a bit later and take questions from those joining us online. If you have any questions, please unmute and ask your question. The chat is sitting somebody. Saying thank you. Done with you.
Oh.
Okay. Any questions from online audience? Okay. Further questions? Yes, please.
I have a question about how many guided scriptures?
Well, it depends. So if in the objective validation part, I think there were 2 gliders and 1 drifter. But in that, so eventually, after you validate in specific instances, when you go to predicting eddies, like Ihapetra eddies, we're talking now about an experiment that can last months, in which you could have 20, 30.
I was wondering if it's possible to analyze what's the margin of improvement after.
Yes, actually, we've done that in sensitivity analysis by controlling the number of drifters, and that has a dramatic effect. The more drifters you have, the better.
Is it possible, for example, to predict how many drifters would want ideally model?
That's an excellent question. We have not looked into that. At the time, yeah, that's it. The time is key.
Right.
And at which time scale?
And they might also start conditions on the distribution because they're all together.
Yeah.
Any other questions?
I think more or less.
Oh.
Will it?
Thank you.
No, thank you.
Thank you.
They're only.
If there are no more questions.
Here, sorry, a non-technical question.
No worries.
So you've collected all or different data depending on how many drifters. Analyze this. And it's super aggressive as far as even though the public dissemination of this information. Would it be possible now to produce, much as they do, I think, for winds, like a
Yeah, so you're
like
talking
a
about the
temporary
real-time
accurate-
products. Yes.
Is there such a thing?
There is, so, but we're not at that stage
Okay.
yet.
But you have that in mind.
We had that in mind, and that, depends on the resources we have, the students we have. But we also have this map in mind, and that's easier, to produce
Right.
maps, for which you don't need to do things real time.
Right.
But just like, for example, capturing that in 2006, so you would produce maps that would evolve from YouTube. That's very useful. But putting this into a product, we're not there.
But you have that in mind. That's all.
Okay, please join me in thanking the.
My pleasure.